Topic 17.1 is looking at equilibrium law. So now that we know how to write an equilibrium expression with the equilibrium constant, we can start to go through and do calculations with that information. This topic 17.1 is split into two videos. This one is calculations and the next one is just relating it back to concepts we've learned previously. Now with the calculations, I'm going to do a slide with just how to set up the calculation and then a slide with the example. You could write just the example, you could write just the how to set it up, or you could do both for whatever you need to do to remember how to set these up. So Kc, as we already know, is your equilibrium constant. It is a quantitative value for the composition of the equilibrium mixture. It is telling you what is more favored, products, reactants, or are they equal in their concentration. For our purposes, we are doing all our calculations with a homogeneous equilibria, which means all reactants and all products are going to be in the same state of matter. First setup, calculating Kc when given the equilibrium concentrations of all your reactants and all your products. We did see this in 7.1 video 2, but we're just going to revisit it here again. First thing you want to do, you want to write a balanced reaction. And I cannot stress enough to say balanced. I have seen questions on the IB exam where they give you a partially balanced reaction. So always just remember, write a balanced reaction. And if they give you a written reaction, make sure they balanced it. Write your equilibrium expression. And then substitute the given values, plug it in your calculator, and solve. So here we have an example. Hydrogen can be prepared by the combination of carbon monoxide and water at 500 degrees Celsius. At equilibrium, the concentrations in the reaction mixture were found to be. And so I'm going to write the reaction first. So we know we have carbon monoxide and water. It is an equilibrium reaction, so we use the double arrows. Hydrogen gas is formed and CO2. Now, if I reread the problem, it said hydrogen can be prepared by the combination of carbon monoxide and water. They didn't tell you that carbon dioxide was a product. You have to go back to your how to write a reaction and how to determine those products to make sure you are accounting for all atoms in the reactants reappear as products. All right, so we have at equilibrium 0.150 for carbon monoxide. We have 0.0145 for water, 0.200 for hydrogen, and 0.0200 for carbon dioxide. So we have step 1. Step 2, write your equilibrium expression. Kc equals products, and there are no coefficients, so it makes it very easy, over reactants. Plug in your information. Plug it in your calculator, and you get 1.84 for your Kc value. So what does this mean? It means your Kc value is greater than 1, which means products are favored. And so now we have quantitatively said that we are favoring the products. Now you could, therefore, draw a bigger arrow pointing towards products, knowing that is the direction of favor. Very simple. Write your equilibrium expression, plug in the data, solve. Now we're going to make it a little bit harder. So calculating the Kc when you're given initial concentrations. So it's essential that you read the question to make sure you are understanding, are you working with initial concentration or the equilibrium concentration? So the steps, once again, write a balanced reaction. Then under the reaction, you're going to write the values that are going to occur within that reaction. So you're going to have your initial concentrations first. And those are going to be the concentrations that are originally placed in the solution or in the reaction. And we're going to assume the products are zero unless otherwise stated. I have seen problems where they give you a product concentration, so they're actually starting with a mixture. So really make sure you're reading the question and you're applying all values appropriately. Then you want to look at what's the change in your concentration. So this is how much is going to react to reach equilibrium. You want to subtract that change from reactants because the reactants are reacting and therefore are disappearing. And you want to add for products because products are being made and therefore are increasing in concentration. Then once you figure out that change, you can have your equilibrium concentration, and that's the concentration present in the equilibrium mixture. Once you have that information, write your Kc expression, substitute the equilibrium concentrations, and solve. Now you'll hear these called ICE tables, and the reason they're ICE, it stands for essentially what goes on that line. I for initial, C for change, E for equilibrium. I actually had a student tell me he does RICE to remember that R is the reaction, I is the initial concentration, C is the change in concentration, E is the equilibrium concentration. Choose one that works for you to help you remember how to set it up. So the example. A student placed 0.2 moles of PCl3 and 0.1 moles of Cl2 into a 1.0 decimeter cube flask at 350 degrees Celsius. The reaction which produced PCl5 was allowed to come to equilibrium. So first thing we got to do, write that reaction. So we had PCl3, gas, reacts with Cl2, gas, and it makes PCl5, gas. Hey, lo and behold, it's already balanced. That kind of makes it easy. So that is our R. On a different color. So now we need to put our I. That is our initial concentration. So a student placed 0.20 moles of PCl3 and 0.10 moles of Cl2. Now the reason we're using moles is because moles is constant for no, so it is a constant value, and so you can compare it between all your compounds. That's why we don't want to use grams. If it's grams, you need to convert to moles. And so then we have 0.0 for our reactant, or our product, sorry. So now we need to determine our change and our equilibrium concentrations. I set this up like a math problem. So the reaction which produced PCl5 was allowed to come to equilibrium, at which time it was found that the flask contained 0.12 moles of PCl3. All right, so you have to be given something. You have to be given the change, or you have to be given at least one value of the equilibrium concentrations, so you know what that difference is. So they gave us the equilibrium value for PCl3. So now we need to determine. We have 0.20, right? And what we have remaining is 0.12. What is that difference? Well, that difference is 0.08. So that is what the change in concentration was. So we want to subtract 0.08, subtract 0.08, add 0.08. And you want to keep that value consistent across all compounds. Now, what you need to keep in mind is if there was a stoichiometric, like balanced reaction, you want to use that coefficient in addition to that change. So an example of that would be, and I'm just making this up at this point, if there's a 2 with that Cl2, we want to do 2 times that negative 0.08 or negative 0.08 because the mole ratio represents that you have to have 2 of those chlorines. So make sure you're paying attention to what that balanced value is. This example is a 1-to-1 ratio. All right, so that chlorine goes to 0.02, and then that ClCl5 increases to 0.08. All right, so now that we have our equilibrium concentrations, these are the values we want to use in our expression. So let's set up our expression. So Kc equals products over reactants. Substitute the calculated values in. And you get 33. So since Kc is greater than 1, you are favoring products. So it's very simple. It's not a very complicated process. So what you need to keep in mind is you need to figure out what that change is. All right? And you need to make sure you are following the mole ratios with that change to get the appropriate amount in that equilibrium expression. So now calculating equilibrium concentration from the Kc. So this means we know Kc, but we're not going to know one of the equilibriums for one of our products or reactants. So there's 2 steps. I know. There's simple and then there's complex. So simple. If you know your Kc and you know all but one concentration, substitute and solve for that unknown. Simple, right? So what does this look like? So we have a reaction. Carbon monoxide reacts with hydrogen to produce methanol. Say what? We saw this in industrial applications. No way. So here's an example of where those 3 reactions in the industrial applications in video 3 of 7.1 comes in, is they tend to use those ones as examples so that you can relate back to them a little bit easier. All right, so this reaction has a Kc value of 0.500 at 350 K. And you're like, why do I care about temperature? Okay, they could say, how does the equilibrium concentration change when the Kc is at 350 K versus 500 K? So then you'd have to compare how the change in equilibrium concentrations and therefore Kc are affected based off that temperature change. Okay, just to let you know. All right, so we know and we are given that carbon monoxide is 0.200 and hydrogen is 0.155 moles at equilibrium. So what is CH3OH? We'll write that equilibrium expression. So Kc equals CH3OH over CO H2, and that H2 has a squared effect because it has 2 in its balanced equation. Now let's substitute. So we know Kc, 0.500. We don't know our methanol, but we do know our carbon monoxide and our hydrogen. All right, so I'm just going to go through all the steps. So I did the math on the bottom, and you get 0.0048, right? And then isolate your CH3OH. So you multiply across, and you get 0.0024. And it would be better to answer it as 2.4 times 10 to the negative third, and depending on sig fig values, there's actually 3 sig fig values, so it's 2.40 times 10 to the negative third moles for your methanol at equilibrium. All right, so it's really no different. You just have to manipulate your calculation a little bit to solve for that unknown. Now you're probably thinking, dude, I got this, right? This is easy. Well, let's just add a little loophole in now. Not a loophole, but a little wrench in the game, and go with the complex version. So you're going to know your Kc, and you're going to know your initial concentrations, not your equilibrium concentrations. So you're going to have to use algebra through this process. Like always, write your reaction. Set up your Rice table, so reaction, initial concentration, change in concentration, and equilibrium, as we did prior. Your initial concentration is given to you. Remember, products, if they're not stated, are going to be 0. Now, what about that change? Because we're not given an equilibrium concentration for any of our reactants or our products. So that means we do not know what that change is going to be. So we have to solve for x. So the change in concentration becomes minus x for your reactants or plus x for your products. And make sure you're still using the mole ratios appropriately, which is right there. Apply your coefficients. And therefore, your equilibrium concentration becomes your initial concentration minus x for reactants and your initial concentration plus x for your products. Write the Kc expressions, substitute the values, solve for x. Now that's going to give you your change in concentration. You are not done yet. Once you know the change, you can then find the equilibrium concentration for each compound. These are a lot of steps, but it's those final compounds, those equilibrium concentrations, that are where the points are at in this type of problem. Okay, so the equilibrium constant Kc for the reaction I'm going to actually give myself a little bit more room. SO3 reacts with NO to produce NO2 plus SO2. The Kc value was found to be 6.78 at a specified temperature. All right, so then that is our reaction. So we need our initial, our change, and our equilibrium concentrations. Okay. So if the initial concentrations of NO and SO3 were both 0.0300, so our products are 0. What would be the equilibrium concentration for each component? So now we have to apply our algebra. So our change is minus x and plus x. Everything is a 1-to-1 ratio, so we don't have to apply any coefficients to those x's. Carry that down, so our equilibrium concentrations become 0.300 minus x. 0.0300 minus x plus x plus x. So now we're going to write our Kc value, or sorry, our Kc expression. So Kc equals NO2 times SO2 over SO3 and NO. Just like before, we are going to substitute in our equilibrium concentrations, even though they are an algebra setup. All right, so that becomes x times x, which is also known as x squared, right? And 0.0300 minus x times 0.0300 minus x. So I'm going to rewrite that as x squared equals 0.0300 minus x squared. And this is equal to 6.78. So now you have to go through and you have to solve this algebraically, right? So the first thing we are going to do is we're going to take the square root of everything to get rid of the square roots that are on your equilibrium expression. And so when you do that, you are going to get 2.60 equals x over 0.0300 minus x. That just makes it a little bit easier. It may not always happen that way, so you have to make sure you're following through with your algebra. So now we just keep going through. So now we need to get rid of that denominator. So then 2.60 times 0.0300 becomes 0.078 minus 2.60x. That equals x. So then 0.078 equals 3.60x, because there's a, remember, a 1 right there. So we got rid of that 2.60 on that side. Divide that by 3.60, and you get 0.0217, and that is your x. But you are not done. All right, so that is not the answer. Okay, so we need to figure out all our concentration. So use that x. So we want to take 0.0300 and take that minus 0.0217. And so our concentration for SO3 becomes 0.083 moles, 0.083 moles, 0.0217 moles, 0.0217 moles. That's your answer. If you don't have a unit, also, you won't get the points. So make sure that you pay attention to the units that are given to you in that problem. Last one is looking at calculating equilibrium concentration from a small Kc value. And this just is a little bit different, and so this is for a reaction that barely gets started. And what does that look like? So the change in the concentration is very little. It's close to 0. Therefore, it's most likely not measurable by any instruments we carry. Therefore, we have to assume that that initial concentration is the same thing as the equilibrium concentration. So you do everything we just did. Set up the rice table, figure out what your initials are, plug in the information, your x's, but that change is going to be equal to the initial concentration is proportional to the equilibrium concentration. So what that looks like. If we have a reaction, 2 H2O decomposes into 2 H2 plus O2. It has a Kc value of 7.3 times 10 to the negative 18. It's a really small Kc value, like really small. All right, a reaction is set up at this temperature with the initial, so let's set up our rice table. So R, I, C, E. Okay. So the initial concentration of H2O is 0.10. Our product's 0.0. Okay, calculate the H2 concentration at equilibrium. So we are looking for this answer right here ultimately. All right, that's all we're given. So we need to go through. And so here we're going to subtract our x, but we have to subtract 2 of them because there's a 2 as a coefficient. We need to add 2 x's due to the coefficient, and then just add 1x. So bring that on down. So you get 0.10 minus 2x, x. Now, due to this extremely small Kc value, we assume that our initial concentration is the equilibrium concentration because it is not measurable to the significant figures that we can do in lab. Therefore, we are going to assume 0.10 is the equilibrium concentration for water. So now we're going to write our expression. So Kc equals H2 squared times O2 over H2O squared. Plug in your values. So 2x squared, and 7.3 times 10 to the negative 18 over times x over 0.10 squared. Okay, so let's go through. I'm going to get rid of that denominator first. So what that looks like, we get 7.3 times 10 to the negative 20 equals 2x squared times x. Well, what does that become? So if we have 7.3 times 10 to the negative 20, 2x squared becomes 4x squared times another x, because then it becomes 4x cubed, right? So then do we divide by 4 and gets 1.825 times 10 to the negative 20 equals x cubed. And then you have to cube everything. And you get, or cubed root, or whatever they call that, right? So then you get 2.63 times 10 to the negative 7 equals x. Look at how small that number is. Now, there was still a change, and that's why we still do this whole process. We still did create some H2 and O2. This is an extremely important process for topic 8, which is why we're learning about it now, so that we don't have to learn it and apply it in topic 8. So if you understand these small Kc values now, it makes what we have to do in topic 8, acids and bases, easier. We are not done. We want that H2 value, right? And so now we need 2 times this. So to get that H2 2 times 2.63 times 10 to the negative 7, and we get 5.3 times 10 to the negative 7th moles. And that is the answer we are looking for. And that's all for the calculations.